All right. Good morning, everyone. So we are recording now, and we are starting our discussion today on how to find a perfect matching in an arbitrary, in a general graph. So basically, we want to focus on non-bipartite graphs. So that's the main question we want to address. Okay. All right. So let's go back to how we did things in the bipartite case. Just because we are essentially going to look at what we did in the bipartite case. It won't work. It will fail for very specific reasons, and we will try to fix that. Right? So in the bipartite case, let's say you have a graph G and you have some matching M. So you look at and you try to find an M exposed vertex. I mean, if there is no M exposed vertex, then you already have a perfect matching. Right? You call that the root of your tree that you are building. You look at a neighbor, and if the neighbor is already matched, then you add the matching edge like this. Right? And you keep doing that. And in particular, we started at a black vertex, which was our color class U in the bipartite case, right? So in the bipartite case, we have U and W. And at every point, we look at a black vertex in our tree. And if it has a neighbor outside the tree, we either find an augmenting path if that vertex is exposed. And if it is not exposed, then it is matched. And we add that vertex and its matched neighbor to the tree, right? All right. And when we cannot build the tree anymore, it means that we have found a deficient set, right? If we can't find an augmenting path and we cannot build the tree anymore, it means we have a deficient set. And the deficient set would be the black colored vertices of the tree, right? That would be our set S. So all these vertices are in S. So let's make that drawing again. So we get a set of vertices. I've made 4 vertices here. And it has 3 neighbors by simple properties of trees, right? By simple property of this particular tree, how it is constructed. And the rest of the graph looks like this, right? As we drew yesterday. We might have like 5 vertices here, in which case we will have 4 black vertices on the bottom. All right. Sorry. Oh, I see. Okay, there is an issue on one of the screens here in the classroom. I'll just pause for a bit. Okay, in the meanwhile, I'll just make some more. Oh, the screen is working. Okay. Okay, now it's working. Thank you. Okay, sorry about that. There was some issue in one of the projector screens in the classroom. Okay. So this is our set If the black vertices are u and the white vertices are w, then this is u minus s, and this is w minus the neighborhood of s. Right? Okay. And yesterday we noted that if we take the bottom left and the top right sets, that is a touch set, right? In this case, we have, sorry, not the bottom left and top right. Sorry, I made a mistake there. I meant the top left and the bottom right. If you look at these 7 vertices in this example, when you delete these 7 vertices, you will get exactly 9 isolated vertices, which will be your odd components, right? And so these sets, n of s union u minus s, is a touch set. So that was the touch set I focused on yesterday. However, from the algorithmic point of view, it is also worth noting that n of s itself is a touch set. If you just look at this set, this is a touch set. Why? Where are all the edges? The edges go from the bottom left to top left, or from the bottom right to top right, or the edges will go from the top left to the bottom right. In particular, there are no edges from the bottom left S to the top right W minus NS, right? And observe that if you think of this as your set Z, so Z is the neighborhood of S. If you delete the vertices of Z, you will have all the vertices of S being isolated vertices in the resulting graph, right? In particular, each one will be a component in itself. So you have deleted 3 vertices and you are getting 4 odd components, right? So observe that this itself is already a touch set, since the graph G minus Z has 4 odd components in this example, and the cardinality of Z is exactly 3. Right? In general, you will have k vertices and you will get k plus 1 odd components. In fact, if you just think about it arithmetically, you will have at least k plus 2 odd components, because the total number of vertices in the graph is even. But that's not important. The main point is that you have more odd components than the number of vertices you have deleted. Okay, so the M alternating tree actually gives you both a deficient set and a touch set. The deficient set is your black vertices in the tree, and the touch set is the neighborhood, which is the white vertices of your tree. Okay. Are there any questions or concerns at this point? So the algorithm we will see for the non-bipartite case, we will try to do one of a few of the same things, right? What we will try to do is we'll try to construct a tree, and we will try to make sure that when we can't find an augmenting path, the white colored vertices of trees are bipartite, so I can still color the vertices white and black, although the original graph is non-bipartite. So we will make sure that the white colored vertices of the tree will still form a touch set. Okay, so that's one of the things we will try to ensure. So our algorithm will try to construct an M alternating tree such that when we can't find an augmenting path, the white vertices of the tree. Another way to think about it is to give levels, right? So this is level 0, this is level 1, level 2, level 3, level 4. So the white vertices will correspond to vertices in the odd levels of the tree. White vertices of the tree, this will be the vertices in odd levels, where the root is level 0. This will give us this will become a touch set in our graph G. Okay. Of course, I haven't shown you the algorithm yet, but I'm just trying to give you a sense of what the algorithm is going to try to do. Okay. The trickier part is finding an augmenting path or concluding that there is no augmenting path. Okay. And we will only focus on examples and intuition today. I won't formalize the algorithm today. Okay. Are there any questions or concerns at this point? All right. If not, I want to now go to some examples. All right. So we are starting a new page, and let me draw one example of a non-bipartite graph. Okay. Let's see. Am I missing some edge? Yeah, I'm missing one edge here. Okay. So let's consider this graph, and let me label the vertices simply using numbers 0, 1, 2, 3, 4, 5, 6, and 7. Okay. So we've got our graph G. At any point in our algorithm, we will have some matching. You could start with the empty matching, or you could start with any maximal matching. So let me start with a particular maximal matching that will illustrate the points I want to make. So here is the matching I want to start with. The edge 1, 2, the edge 3, 4, and the edge 5, 6. Okay, this is our initial matching. Okay, and we want to build our alternating tree as we usually do and see if we can find an augmenting path using that approach. Okay. All right. So let us build an M alternating tree. T. And this tree, we will have vertices. Let me not give it a notation. We will refer to the vertices in the even levels, so 0, 2, 4, and so on. We will refer to them as the set U, and the vertices in the odd levels, we will refer to them as the set W. Okay. Let me start at some M exposed vertex. Let's say I start at 0. Okay. Before we proceed, can somebody tell me by observation, do you see an M augmenting path? Does anybody see an M augmenting path here? Just to get a sense of what we are expecting. Yes, 0, 2, 1, 4, 3, 6, 5, 7. That is actually an M augmenting path. We have got a matching of size 3 here, cardinality 3. When we augment on that path, so you take the symmetric difference, we will get a matching of size 4. This graph has 8 vertices, therefore that will become a perfect matching, right? So we are expecting to find an augmenting path and not a touch set. Okay, cool. All right, so let us just write this down. Observe that there exists an M augmenting path and therefore a perfect matching because the graph only has 8 vertices. And in particular, there does not exist a touch set, right? Because if there is a perfect matching, you can't have a touch set. Okay. All right, so that's just an observation. But of course, we don't want to observe in general. We want to come up with um, a procedure that will always work, right? A systematic method of doing things. Okay, so let's start at vertex 0 and let's look at some neighbor. So let's look at the neighbor 2. Well, the neighbor 2 is a matched neighbor. So I will add it, and I will also add 2's matched neighbor, which is 1. Okay. So I've added 2 and 1 to the tree. And let me color these even level vertices black, and let me keep the odd level vertices as white. Okay. So these black vertices are going to be our set U, and the white vertices are going to be our set W in the tree. Okay. Okay, now let's try again. Let's look at other neighbors of 0. Well, another neighbor of 0 is the vertex 3. So, and it is also matched. So let me add both of those to the tree. So we got 3 and its matched neighbor is 4. Okay. Now let us see what we can do. So again, we want to build the tree further by looking at the U vertices and see if they have any neighbors outside the tree. So 0 has only 2 neighbors in the graph G, 2 and 3. They are already in the tree. 1 has 2 neighbors, 2 and 4. They are already in the tree. And 4 has neighbors 1, 2, and 3, and all 3 of them are already in the tree. Okay. So at this point, the U vertices do not have any neighbors outside the tree vertices. Are there any questions or concerns at this point? Is everybody with me? Okay, good. All right, so if we were in the bipartite case, we would look at the vertices 2 and 3 and we would conclude that this is a touch set. Or we would look at the vertices 0, 1 and 4 and we would conclude that it is a deficient set. But remember, now we want to think about touch sets, right? So let's look at the vertices 2 and 3 in this case. Well, let's see what happens. Supposing I observe the vertices 2 and 3. So imagine that we are deleting these 2 vertices from the graph. Of course, we know that there is no touch set in this graph, but let's just verify it visually, what's going on. So if I delete 2 and 3, can somebody tell me if there is any component in the graph, or is it a connected graph, or do we get a disconnected graph? Imagine G minus 2, 3. I'm not going to draw it. I want you to observe it and imagine what happens when you delete 2 and 3. Disconnected graph. Can you give me one component? 1, 4 is a component. 1 and 4 are joined by an edge, and that is one component. It is an even component. What about another component? Anybody in the call?
So 5, 7.
5, 7. Do you want to include one more vertex?
6 as well.
5, 6, and 7. 5, 6, and 7, they are connected to 2 and 3. So that will become a single component. That will be an odd component. And there is yet one more component, right? Anybody sees that? 0, right? 0 is a third component. So we have got 2 odd components, 0 and 5, 6, 7. And we have got one even component, 1, 4. So this is not a touch set, right? Because we are deleting 2 vertices and we are getting 2 odd components. We want more than 2 odd components. Okay, fair enough. We did not expect a touch set, so it is not a touch set. Okay. It would, however, be a touch set if the vertices 1 and 4 were not connected. Observe that it would be a touch set if 1 and 4 were not connected by an edge, which would happen in a bipartite graph because they are both black colored vertices in the tree that you have constructed, right? So in a bipartite graph, the U vertices will form a stable set in your tree because they are all the same color. And so the W vertices will form a touch set, because when you delete the W vertices, you will get as many odd components as the number of vertices in U, which is exactly W plus 1, cardinality of W plus 1. Okay, so you would delete 2 vertices and you would get 3 odd components. But this is not the bipartite case. We have a situation here which is the edge 1, 4 joining these 2 black vertices. Let me call this edge E. Okay, is everybody with me? Yeah. So in the non-bipartite case, we cannot conclude that just because we are not able to build the tree any further, we have found a touch set, right? In fact, as we know, in this case, we have an augmenting path and a perfect matching. So how do we get that? All right. Are there any questions or concerns? Okay. So basically, the augmenting path algorithm was known since Agarwal's days, right? Which was 1930s. And in fact, it might have been known even earlier. And people were trying to find a similar M alternating tree or finding an M augmenting path approach for non-bipartite matchings, non-bipartite perfect matchings, right? But people did not know how to deal with this situation when you have 2 vertices in U joined by an edge, right? Okay, so it took Jack Edmonds to come along in 1965, and he took a leap of faith, and I want to explain that. So Edmonds' idea, so what Edmonds said is that if you find 2 vertices in the set U in your tree that you are constructing, right? So 2 black vertices joined by an edge, shrink the cycle. Observe that the tree plus the edge E will have a unique cycle. Any tree, if you take a tree and you add one more edge joining 2 vertices of the tree, it is easy to see that there will be a unique cycle in the tree, because there will be a unique path joining the 2 ends of the edge, right? So if the edge E is U and V, then in the tree you will have a unique path joining U and V, and that path along with the edge will give you a cycle. In particular, because you are connecting 2 black colored vertices, you will get an odd length cycle, okay, which you expect to see in a non-bipartite graph. What makes a graph non-bipartite is the existence of odd cycles. So Edmonds said, if you have such an edge joining 2 black vertices in your tree, take the unique cycle in T plus E and shrink it to a single vertex, okay, and try to work with the new graph. Okay, so that's what we are going to do. So what he said is, observe that T plus E has a unique cycle, and let's say E is equal to UV, where U and V are both black colored vertices in your tree. In particular, let's call this cycle Q. In particular, Q is an odd cycle because you have joined 2 black colored vertices, right? So his idea was shrink Q into a single vertex. Let's call it little q. Okay. All right. So we will shrink this cycle into a single vertex in both the graph G and in the tree that we have constructed so far. Okay. This is a particularly simple example because the tree is basically, the tree's vertices are exactly the same as the cycle's vertices. I will show you a more non-trivial example in the next example. Okay. So in this particular case, the vertices of the tree is equal to the vertices of Q. So in this example, okay. All right. So let's draw the graph G prime. The graph G prime is going to be the same as the graph G, where we shrink the vertices of Q into a single vertex little q. That is the notation I'm going to use. Okay, so this is a notation. It means that shrink all vertices in the set PQ into a single vertex Q. And any edges between the vertices of Q, you delete them. So I'll just draw and we will write formal definitions tomorrow, right? Right now, let me just draw the graph so that you get a sense of what this means, right? So we are shrinking 0, 1, 2, 3, 4, all these vertices into a single vertex. So in our case, we will get a single vertex, little q, and this little q will be joined to 6 and to 5 because of these edges. Notice that 3 joins to 6, 3 joins to 5, and 3 is in q. So now that edge will go to the shrunken vertex. And there is also an edge from 2 to 6, which will basically become another edge from q to 6. But we don't care. We will delete this. We don't keep, we are looking at simple graphs. So we won't care about extra edges joining little q and some vertex in the complement. Okay. And we have a vertex 7. And 7 is joined to 5 and 6. And 5 and 6 are joined to each other. Okay. Let me also just show you by, so what we have done is we have taken this entire set This is the set vertices of Q, and we have shrunken it into a single vertex little q. Okay. Are there any questions or concerns regarding this operation? We will write down the formal definitions tomorrow. Right? Okay. So we get this G prime. What about the matching? We should also modify the matching, right? So the matching is going to be quite straightforward. We will just keep the matching edges that were not already in the tree. Right? So our M prime is simply going to be one edge, which is the edge 5, 6. Okay. So whatever edges were not in the vertices of Q, they did not have both ends in Q, we will keep those edges as they are, right? And Q will become an unmatched vertex. All right. Actually, let me not say that. Q need not become an unmatched vertex. We will see another example tomorrow. So yeah, I'll take that statement back. Q might be matched or unmatched. It depends on the situation. But in this particular example, it is going to be an unmatched vertex because there is no matching edge incident on the vertices of Q going outside of Q. Right? All right, so that is our G prime. Our M prime is simply the edge 5, 6. And what about the tree? Well, in the tree, we are going to do the same kind of thing. Instead of this 5 vertices, we will think of it as a single vertex. Okay, so in this particular example, the tree just becomes a single vertex, which will be little q. So the tree, sorry. So the tree is just one vertex, that is q, and that is our exposed vertex. Okay, so I'm going to color it black as usual. All right. And now let's try to again build our M alternating tree in this new situation, right? So now we have a different graph, G prime, M prime is the matching, and T prime is the alternating tree with respect to this matching. So let's try to build this tree. let us build or let us extend. Okay, so let me just redraw here. So we are starting with the vertex Q. Let's look at its neighbor. So let's say I find the neighbor 5. Well, 5 is already matched, so I will add both 5 and its matched neighbor 6. Okay, and now Q's two neighbors are 5 and 6, which are already in our tree T prime, right? And 6 has a neighbor 7, which is exposed. So what we have here is an M augmenting path in this graph, right? So what we have is P prime, and that is an M prime, sorry, not M, it is an M prime augmenting path in G prime. Okay. So we don't have an M augmenting path in the original graph G, but what we have found is an M prime augmenting path in the derived graph G prime, which we derived by shrinking this odd cycle, doing this odd cycle shrinking business. Okay. All right. So can we somehow extend this M prime, P prime to an augmenting path in the original graph with respect to the original matching M? That is the question. So can we extend P prime to an M augmenting path P in the graph G? Okay, so let's see. We have 5, 6, and 7. So we want to take that stuff, right? All right, let me see how to explain this part. Okay. Okay, so, right. So here is what we are going to do. We are going to go back to our tree T. Maybe not. So let's look at this tree and let us blow up the vertex Q back to the original 5 cycle. Okay. So how did we get T prime from T? We shrunk this cycle into a single vertex. Now we want to do the reverse operation, right? Let us blow back this little vertex Q back to the original cycle it was and see if we can somehow find an augmenting path in that graph. Okay. So what happens? So I'm going to replace this Q by this 5 cycle, 0, 1, 2, 3, 4, right? But where should this edge go? Q to 5. Well, Q to 5 corresponds to this edge joining the vertex 3 and vertex 5, right? That is how we got the edge Q to 5 in our graph G, right? So if we do that, we basically get something like this. I'm making a drawing here. So we have got 5, 6, and 7. And 5 to 6 is a matching edge. Five to 6 is a matching edge, right? So let me just put this part in a green color so that we know what it is referring to, right? So what we have done is we have taken the tree T prime. So this is our T prime. And we have blown up the vertex Q into the original 5 cycle. And if you do that, you get this graph. And this is the part which is coming from T prime. Okay. And observe that here we can actually get an augmenting path. Does anybody see it? Yeah, go ahead. Exactly. So what we will do is we will start from the odd cycle. So in the odd cycle, we have two ways to get from 0 to 3. Either we directly take the edge 0, 3, but that doesn't give us an augmenting path. But if we go through the other side, 0 to 2 to 1 to 4 to 3 to 5 to 6 to 7, we get an augmenting path. Okay? And that is exactly what we will do. So for augmenting path, we will traverse the odd cycle in a particular way. There are only two ways to traverse. There's not 1,000 ways to traverse, right? And then we will take the path we have already found. Okay? So the augmenting path we get is exactly 0 to 2 to 1 to 4 to 3 to 5 to 6 to 7. All right. So the point is, whenever you do this shrinking operation, shrinking this odd cycle operation, and you get this derived graph and you construct this alternating tree T prime with respect to the matching M prime. If you find an augmenting path with respect to M prime in the derived graph G prime, then you can translate that to an augmenting path in the original graph with respect to the original matching by traversing the odd cycle in one of two ways. Okay, we haven't proved things, but hopefully in this example you can see what's going on, and it turns out that it's not a coincidence. Okay, so again, this is a small example. I'll show you a more complex example tomorrow. The trouble I'm having is that I'm not finding any good examples in any of the books I'm following, so I have to basically construct my own examples. Right, so in this example we started with a matching with three edges. We did this M alternating tree construction. We ran into an issue. We were not able to construct the tree any further, and the reason was, but at the same time we could not find a touch set, because the black vertices in the tree, they did not form a stable set, unlike the bipartite case. So one of the edges, E, with the ends 1 and 4, we took that edge joining the two black vertices. We took the odd cycle that is created by adding that edge to the tree, the unique odd cycle, and we shrunk it into a single vertex, and we got a derived graph G prime. We also modified the matching accordingly, and we also shrunk that 5 cycle in the tree, those 5 vertices, into a single vertex to get our T prime. And then we built T prime further, and we got an augmenting path M prime, P prime, with respect to the matching M prime. And we went back to the original tree by blowing up the little q into the 5 cycle, right? So we went back to that graph. It is not really a tree because it has one more edge, right? And there we were able to find an M augmenting path using our M prime augmenting path. Okay, good. I want to show you one more example. So in this example, we found a perfect matching because we found this augmenting path. We augment and we will get a matching with 4 edges and the graph is 8 vertices. So that is a perfect match. Okay. So this is an example of a graph that has a perfect match. I want to quickly show you one more example where we don't find a perfect matching, but instead we want to find a touch set. Okay. Are there any questions or concerns? Right. Vertex 1. Then you would still find it, right? Oh, sorry. So I didn't get the last part. If you can't find an augmenting path, then right, right. No, we'll see an example. So if we find an augmenting path, so his question is, I don't know how to phrase it in a short way. Um, so the first question was about the placement of the M augmenting path, right? P prime. So it turns out that no matter where you place it, you will be able to traverse the odd cycle in one of the two ways to still get an augmenting path in the original graph. So we will prove that, right? And when you can't find an M prime augmenting path in the derived graph, right? Also, I should repeat that we might be doing this derived graph process repeatedly. So it's not just one time that we are doing it. It is possible that in G prime, we would have again found an odd cycle, we would have again shrunk it, and we would have gotten a G double prime. And so then we would have to come back 2 steps, right? So it is a recursive algorithm. And in this particular case, we only had one recursion level in some sense, right? Um, but when you can't find, okay, so what will happen is when you get an alternating tree where all the vertices in the set U, the black colored vertices, they form a stable set. At that point, you will be able to find a touch set in the original graph. Okay. I want to show you an example where this actually happens. So let's see how much more time we have. Let's try to see if we can complete this example. Right. Okay, so let's do an example where we find a touch set so that we also get a sense of the alternative situation. All right, so here is the graph I want to show you. Um, okay, let's label the vertices 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so we've got 12 vertices. All right, and let's start with a particular matching. So we've got 8, 9, 0, 3, 1, 5, 2, 7, and 10, 11. Okay, so that's our graph G, and we have got our matching M in the red color. Okay, all right, so let's try to build our M alternating tree. Let's start at the vertex 4. So let's look at the neighbors. 4's got one neighbor 8, and 8 is already matched to 9. So let me add both those vertices to my tree. Okay. 4 has got another neighbor 0, which is matched to 3. So let me add both of them. 0, and let's say this is 3. Let me also color these vertices. Um, so this is black, this is black, this is black. All right. 4's got one more neighbor, 1, which is matched to 5. Okay, good. At this point, 4's neighbors are basically exhausted. They are all in the tree already. They are 0, 1, 8, and 9. And 9, 3, and 5, their neighbors are also, I believe, exhausted. No, actually, that's not true. 9 has only 4 and 8. They're already in the tree. 3's got more neighbors. No, 3 has got neighbors 0 and 1. They're already in the tree. 5 has got more neighbors. Okay. 5 has neighbors 0, 1, and 2. And 0 and 1 are already in the tree, but 2 is not in the tree. So let's go further. Okay. And 2 is matched to 7. So let's add that. Okay. And 7's neighbors are 0 and 1 and 2, which are already in the tree. So observe that at this point, all vertices, maybe I'll put it differently. No vertex in U, no vertex in U, which is the black colored vertices, has a neighbor outside the tree, right? 4, 9, 3, 5, and 7, all of their neighbors are in this tree already. Okay. And okay, so we can't build the tree in the usual way any further. And sorry, 2, yeah, the black vertices, right? So the white vertices could have neighbors outside, but we build the tree by looking at the black vertices, right? That's how we are building this tree. So the black vertices don't have any neighbors outside the tree. So we can't build the tree in the usual bipartite sense. And in particular, if the black vertices formed a stable set, then the white vertices would form a touch set. However, the black vertices do not form a stable set because there is an edge between two black vertices. Can anybody tell me? There is an edge between two of the black vertices. 4 and 9, right? So in this particular case, 4 and 9, there is an edge E joining them. Okay. So what Edmonds is going to say is you shrink this odd cycle into a single vertex, right? So our cycle Q is 4, 8, 9. This is our cycle Q in the original graph, right? So we shrink Q and we get the graph G prime as follows. So one easy way to draw G prime is to first draw everything that is not in Q and then to put the vertex Q, little q. Okay, so let's do that. So we have got 0, 1, 2, we've got 5 here, we've got 6 here, we've got 3 here, we've got 10 and 11, and we have got 7 joining to 1 and 2. Okay, and we have the little vertex Q, which has two edges going to 0 and 1 to 1. So that is our G prime. The M prime is also quite easy here. It's 0, 3, 1, 5, 10, 11, and 2, 7. Okay, good. All right, that is our M prime. And now let's look at the tree. Oh, by the way, what happens to the tree this time? So the tree is also going to modify in a more interesting way than the last time. So in the tree, we will simply replace 4 at 9 by a single vertex, Q. Okay, so we will have the root will become Q in this example. And the rest of the tree, we will draw as it was. 0, 3, I will put the red colored edges later. Q to 1, 1 to 5, 5 to 2, and 2 to 7. And let me now put the red colored edges. Observe that these red colored edges are exactly the red colored edges in M prime. They are also red colored in M prime, right? So they are edges in M prime. 0, 3, 1, 5, and 2, 7. Okay. All right. So now can we build this tree any further? Okay, so I think we are already beyond time here. Um, I hate to go so much over time, but at the same time, I don't want to. Okay, let's see. Let's see if we can conclude quickly. So Q corresponds to 4, 8, and 9. Okay, observe that in the graph G prime, the black colored vertices, which is little q, 3, 5, and 6, they have no neighbors outside, and they actually form a stable set. Okay, so we are basically at the end of this example. Observe that U, let's call this U prime because it is in T prime. This is the set Q, 3, 5, and 7. This is a stable set in the graph G prime. Okay, there are no edges between these vertices. Observe that. And no vertex in U prime has a neighbor outside the vertices of T prime in the graph G prime. Okay. So we have reached a similar situation to the bipartite case, right? We have a situation where the black vertices, they are obviously not connected with each other in the bipartite case, but that's also true in this example, in this G prime, T prime. And at the same time, the black vertices do not have any neighbors outside. The black vertices of the tree have no neighbors outside the tree. At this point, we will conclude that 0, 1, and 2, the white vertices, they form a touch set in the original graph G. So we'll discuss this more tomorrow. I don't want to, maybe I'll just leave it to you to think about it. So note that the set W prime, which is the white vertices in T prime, which is 0, 1, and 2, is a touch set not only in the graph G prime, but also in G. And I want you all to think why. Okay. So this is a situation where we find a touch set and we know that the graph doesn't have a perfect matching. Okay. All right. So I want to do more complicated example tomorrow. The issue is that I have to basically construct this example myself because I can't find good examples anywhere. So I'm going to work on it and we will see a more complex example tomorrow. All right. So that's all for today. Thank you. Are there any questions or concerns? I'm going to stop recording, but I'm still here if there are any questions.